On the night of April 29th, something happened in the sky above Earth that stopped people in their tracks. Across backyards and balconies, from rooftops in Tokyo to open fields in Texas, ordinary people looked up and saw something that felt almost too beautiful to be real. The Moon, Venus, and one of the most ancient and beloved star clusters in all of human history had gathered together in the same small patch of sky, close enough that you could cover all three with the palm of your outstretched hand. No telescope required, no special equipment, just eyes and a clear night and the willingness to look up. NASA called it a stunning celestial alignment. Astronomers around the world rushed to their cameras. Social media filled within hours with photographs that looked more like digital paintings than real snapshots of our actual sky. And sitting at the center of this gathering, quietly dazzling anyone who knew where to look, was a star cluster so old, so storied, and so deeply woven into human culture that civilizations on every single continent had given it a name long before the first written language ever existed. The Pleiades, 7 sisters, a winter lantern, a celestial calendar, a mystery that human beings have been staring at for at least 100,000 years. But here is where this story takes a turn that even veteran astronomers did not see coming. Because on the same week that the world was marveling at this beautiful alignment in the night sky, a team of scientists quietly announced something that rewrote what we thought we knew about the Pleiades themselves. Hidden inside that cluster, tucked away in regions of space we'd never examined carefully enough, were thousands of stars that nobody knew existed. Thousands of them. New stars. Ancient stars that had been there all along, invisible to us until now, suddenly revealed by instruments powerful enough to see what human eyes, and even older telescopes, had always missed. Scientists just spotted something impossible hidden near Venus. And the deeper you go into this story, the stranger and more wonderful it becomes. To understand why the April 29th alignment was so remarkable, you first need to understand what was actually lining up, and why those 3 specific objects sharing the same patch of sky is not something that happens every night, or every year, or even every decade in quite the same way. Start with the Moon. Our Moon orbits Earth roughly once every 27 days, tracing a path through the sky called the ecliptic, the great highway of the solar system, along which the planets and the Sun also travel. As the Moon moves along this path, it passes near different star clusters and planets at different times of the month. Once each month, the Moon swings through the part of the sky occupied by the Pleiades, sliding past those ancient stars and sometimes, if the geometry is just right, passing close enough to make the encounter visually spectacular. Now add Venus. Venus is the second planet from the Sun, and it is the brightest object in the night sky after the Moon itself. From our perspective on Earth, Venus never strays very far from the Sun. It appears either in the western sky after sunset, what ancient skywatchers called the evening star, or in the eastern sky before dawn, the morning star. Because Venus hugs close to the Sun's apparent position, it only occupies a limited band of sky, and it only occasionally finds itself near the Pleiades at the same moment the Moon is also making its monthly visit. That triple coincidence, Moon and Venus and Pleiades all converging at once, is what makes an alignment like the one on April 29th special. It is not impossible, it is not supernatural, but it is genuinely rare in the way that all perfect coincidences are rare. The ingredients exist, the timing just has to cooperate. And on that April night, the timing cooperated beautifully. Observers in the northern hemisphere who stepped outside in the early evening, in the hour or two after sunset, would have seen Venus blazing low in the western sky, unmistakable, far brighter than any star, with a faint bluish-white intensity that seems almost electric against the darkening blue of twilight. Above and slightly to one side of Venus, the Moon hung in its crescent phase, a thin curved sliver of silver light, the dark portion of its face faintly visible in the phenomenon called Earthshine, where light reflected from Earth's own surface illuminates the Moon's night side with a soft ghostly glow, and there, draped between them and just beyond, was the Pleiades. Depending on the darkness of your sky and the sharpness of your eyes, you might have seen 6 of the cluster's brightest stars, or perhaps all 7, arranged in their characteristic little dipper pattern, their combined light giving the cluster a misty, luminous quality, as if someone had breathed a small warm cloud into the cold of the cosmos. 3 objects, 1 small patch of sky, 100,000 years of human wonder condensed into a single evening. People have always loved the Pleiades in a way they have not quite loved any other star cluster. Part of it is visibility. The Pleiades are among the easiest deep sky objects to spot with the naked eye, sitting roughly 440 light-years from Earth, close enough on the cosmic scale to appear reasonably bright, and compact enough that they fit together in a pleasing tight group rather than sprawling messily across a wide field of view. But the love goes far deeper than convenience. The Pleiades appear in the mythology of ancient Greece, where they were said to be the 7 daughters of Atlas and Pleione, transformed into stars by Zeus to save them from the eternal pursuit of the hunter Orion. The cluster appears in the Book of Job. It appears in the poems of Sappho. The ancient Egyptians aligned the entrances of certain tombs with the Pleiades rising. Aboriginal Australians told stories about the cluster for at least 30,000 years. The Maya incorporated the Pleiades into their calendar. The Pleiades have been found carved into the walls of the Lascaux cave paintings in France, in markings that may be at least 17,000 years old, making them possibly the oldest known star map in human history. The Japanese call the cluster Subaru, and if that word sounds familiar, it is because the car company took its name from the Japanese name for the Pleiades, and the logo, those 6 stars arranged in a cluster, is exactly what you would see if you looked up on a clear night. 7 sisters, 6 visible stars. Where did the 7th go? This is a question that has haunted skywatchers for millennia, and it shows up in the mythology of cultures on nearly every continent. Many traditions describe the Pleiades as 7 sisters and offer some story to explain why only 6 are visible now. The Greeks said one of the sisters, Meropeia, hides her face in shame because she alone married a mortal man while her sisters all married gods. Other cultures say one sister is weeping or hiding, or has gone to mourn some great loss. Modern astronomy offers a more prosaic explanation. The cluster does contain 7 traditionally named bright stars, but one of them, the one the Greeks called Pleione, is close in the sky to another star called Atlas, and can be difficult to separate from it with the naked eye. In certain atmospheric conditions and for certain observers, only 6 are easily visible. The mystery of the lost sister is really just a mystery of human visual acuity and the limitations of unaided eyes trying to resolve closely spaced objects. But the Pleiades, it turns out, are not finished surprising us, because the 7 sisters that ancient humans could see with the naked eye, and the few hundred stars that older telescopes could count, represent only a tiny fraction of what is actually there. The new discovery announced around the same time as the April alignment fundamentally changes the picture. For decades, astronomers estimated that the Pleiades cluster contained somewhere between 800 and 1,000 stars. That was the working number, the figure in textbooks, the statistic that educators used when explaining the cluster to students. The Pleiades had roughly 1,000 stars. That was the story. It was wrong. Using modern instruments capable of detecting extremely faint sources of light, including stars too dim, too small, or too obscured to register on older equipment, astronomers conducting systematic surveys of the Pleiades region began turning up stars that had simply never been catalogued before. Not a few extra stars, not a modest correction to the old estimate. Thousands of previously unknown stars scattered throughout the cluster and its surrounding halo of space, adding up to a population that is dramatically larger than anyone had previously appreciated. Think about what that means for a moment. The Pleiades is not some remote, poorly studied region of the galaxy. It is one of the most observed, most photographed, most analysed star clusters in the entire sky. Astronomers have pointed their instruments at it for well over a century. It sits close enough to Earth that we can study it in considerable detail. And yet, hidden within it, invisible to everything we had used to look at it before, were thousands of stars we did not know existed. It is a reminder that the universe does not reveal itself all at once. Every time we build a more sensitive eye, we find that the sky contains more than we imagined. This has been true since Galileo first turned a crude telescope toward the heavens and discovered that the Milky Way, which the naked eye sees as a faint smear of light, resolves into countless individual stars. It was true when astronomers first turned radio telescopes toward the sky and discovered entire populations of objects that emit no visible light at all. And it is true today as instruments capable of detecting the faintest infrared whispers of starlight reveal that even our closest, most familiar neighbours in the cosmos are richer and more complex than we knew. The newly discovered stars in the Pleiades are mostly what astronomers call low-mass stars, objects smaller and cooler and dimmer than our Sun. Some are likely what are called brown dwarfs, objects that form the way stars form, from collapsing clouds of gas and dust, but that never accumulated quite enough mass to sustain nuclear fusion in their cores. They are the almost stars, warm and faintly glowing but technically not burning in the way that true stars burn. They exist in a twilight zone between stars and planets, too big to be one, and not quite big enough to be the other. These kinds of objects are notoriously difficult to detect across interstellar distances. They produce so little light that finding them requires patient observation with sensitive instruments, careful analysis to distinguish them from background sources, and statistical techniques to separate genuine cluster members from unrelated objects that happen to lie in the same direction but are actually much closer or much farther away. The fact that we are now finding thousands of them in the Pleiades is partly a story about how good our instruments have gotten, and partly a story about how much patience and care went into this particular survey. The astronomers who conducted this work did not stumble onto these stars by accident. They designed a systematic search specifically intended to find the faint end of the cluster's stellar population, the small and the dim, the easy to miss, the ones that previous surveys had simply not been sensitive enough to detect. What they found exceeded their own expectations. Now you might be wondering what any of this has to do with Venus, the planet that blazed so brilliantly in the April sky, close enough to the Pleiades to share the same naked eye field of view, close enough that photographs showed all three objects, Moon and Venus and cluster, together in a single frame. The connection is partly one of timing, a cosmic coincidence that brought the new science and the beautiful spectacle into the same news cycle, the same week, the same headlines. But it is also something deeper than coincidence. Venus has a complicated relationship with the Pleiades in the history of human skywatching. Ancient Mesoamerican astronomers, particularly the Maya, tracked the movements of Venus with extraordinary precision. They knew its synodic period, the time it takes for Venus to return to the same position relative to Earth and the Sun, to within a fraction of a day, and they paid particular attention to the moments when Venus passed near the Pleiades, using those passages as key reference points in their astronomical calendars. In the Mayan tradition, the heliacal rising of the Pleiades, the moment in the year when the cluster first becomes visible in the pre-dawn sky, after a period of invisibility, was an event of profound ceremonial importance, and when Venus happened to be near the Pleiades at that moment, the significance was compounded. These conjunctions were recorded, tracked, predicted, and incorporated into ritual practice across centuries. The Maya were not alone in this. Many ancient cultures saw Venus and the Pleiades as connected, as paired symbols with related meanings in their cosmological systems. The visual logic is easy to understand. Both Venus and the Pleiades are prominent attention-grabbing features of the night sky. Both follow predictable cycles, and occasionally, as happened on April 29th, they appear together in a way that seems almost deliberately arranged, as if the sky itself is making a point. Of course, the sky is not making a point. The alignment is a geometric accident, the product of orbital mechanics, and the particular vantage point of our small planet as it circles its star. Venus is an entirely different kind of object from the Pleiades, a rocky world about the same size as Earth, covered in a dense atmosphere of carbon dioxide thick enough to crush a submarine, hot enough on its surface to melt lead, a hellish place that is simultaneously our nearest planetary neighbour and one of the most hostile environments in the solar system. The Pleiades stars are 440 light-years away. At that distance, the light we see from them tonight left those stars before Shakespeare was born, before Columbus crossed the Atlantic, before the printing press existed. Venus, by contrast, is never more than a few light minutes away. When you look at Venus, you're seeing light that left its surface maybe 2 or 3 minutes ago. When you look at the Pleiades, you're seeing light that has been travelling through space for 4.5 centuries. They share a patch of sky only because of perspective, the way two buildings in a city might appear to stand side by side when viewed from a certain angle, even though one is right next to you and the other is miles away. But perspective matters. Perspective is, in a very real sense, the whole story of how human beings relate to the sky. We cannot feel the distances. We cannot directly perceive the difference between light that is 2 minutes old and light that is 440 years old. What we perceive is the view from our particular vantage point, and from that vantage point, on the night of April 29th, Venus and the Moon and the Pleiades were together, and it was beautiful. This is perhaps the most profound thing about the alignment, and about events like it. They are scientifically explicable. They are the products of understood physical laws operating on known objects in a mapped solar system, and yet they retain the power to stop people in their tracks, to make ordinarily distracted humans put down their phones and look up, to inspire the same feeling of wonder that moved the ancient Egyptians to align their tombs with the rising of the Pleiades, that moved the Maya to track Venus across decades and centuries, that moved some anonymous human being 17,000 years ago to scratch the pattern of those 7 stars into the wall of a cave. We have not stopped looking up. We have just gotten better at understanding what we're seeing, and sometimes understanding something does not diminish its beauty. Sometimes it deepens it. Consider what we now know about the Pleiades. When you look at that hazy little cluster, you are not just seeing a pretty arrangement of stars. You're seeing the aftermath of a star-forming event that began roughly 100 million years ago, when a massive cloud of gas and dust began to collapse under its own gravity and fragment into individual protostars. The cluster we see today is what those protostars grew into, and it is still young by stellar standards, young enough that the hot blue stars at its centre have not yet burned through their fuel and died. The bluish colour of the Pleiades' brightest stars is itself a clue to their nature. Hot stars burn blue, cooler stars burn yellow or orange or red. Our own Sun, at a surface temperature of about 5,500 degrees Celsius, burns a relatively modest yellow-white. The brightest stars in the Pleiades are significantly hotter, burning at temperatures of 15,000 degrees or more, which gives them that faint bluish quality visible to careful, naked-eye observers and obvious in photographs. Stars that hot and that massive burn through their fuel rapidly. On the cosmic timescale, they are mayflies, brilliant and brief. The blue stars of the Pleiades, already 100 million years old, may have only another few 100 million years before they exhaust their fuel and end their lives in spectacular fashion, either exploding as supernova or collapsing into dense remnants. The newly discovered low-mass stars, the dim ones that recent surveys have revealed, will outlive their brilliant siblings by billions of years. A small, cool red star can burn steadily and quietly for 100 billion years or more, long after our own Sun has swollen into a red giant and consumed the inner planets. In the Pleiades, the flashy and the humble exist side by side, the blue giants blazing their way through brief spectacular lives, and the tiny red stars quietly burning, patient and persistent, in the dark between them. Now that we know thousands more of those quiet stars exist in the cluster than we previously thought, we have to revise our understanding of how the cluster formed, how it has evolved, and what it will look like in the distant future as its massive stars die, and its small stars endure. This kind of revision is not unusual in astronomy. It is, in fact, the normal mode of scientific progress in this field. Almost everything we know about the universe has been revised at some point, usually in the direction of greater complexity, greater size, greater age, and greater strangeness than earlier estimates suggested. The universe keeps turning out to be more than we thought it was, and the Pleiades, in their quiet way, have now done this again. There is a version of this story that could feel humbling in a discouraging way. If we did not know about thousands of stars in one of the most studied clusters in the sky, what else are we missing? If our picture of even our nearby cosmic neighbourhood was this incomplete, how much can we really trust our broader understanding of the universe? But that is not the right way to read the situation. The better reading is this. We built better instruments, and we looked more carefully, and we found things we did not know were there. That is the whole project of astronomy, and science generally. You look as carefully as you can with the tools you have. You find what you can find, and then you build better tools and look again, and you find more. The discovery of thousands of new stars in the Pleiades is a success story, not a failure. It is evidence that the project is working. It is evidence that the sky still has things to teach us, even in the places we thought we understood well. On the night of April 29th, while millions of people around the world looked up at the beautiful coincidence of Moon and Venus and Pleiades gathered in the evening sky, they were looking at a cluster that is richer and more complex than the astronomers who first pointed serious telescopes at it ever knew. The people who photographed that alignment and posted the pictures online were capturing light from thousands of stars they could not see, had never heard of, stars whose existence was being written into the scientific record for the first time in human history during that same week. There is something moving about that. Standing in a backyard or on a balcony or in an open field, looking up at a smear of light that the naked eye barely resolves into individual stars, and knowing that embedded in that soft glow are not 7 stars as the myth-makers thought, and not 1,000 stars as the astronomers thought until recently, but a whole population of stars far larger and stranger and more various than anyone who named the Pleiades, in any language, in any century could have imagined. The Seven Sisters have a lot more family than anyone knew, and Venus, blazing nearby in its indifferent brilliance, has been there for every chapter of this story. Ancient people watched it rise and set and tracked its cycles, and wove it into their myths and their calendars and their understanding of how the sky worked. Modern people photograph it with their phones and post the pictures online and read the next morning about what astronomers have just discovered. The technology changes, the instruments change, the understanding deepens and broadens and revises itself. But the looking up does not stop. It has not stopped in 100,000 years, and it did not stop on April 29th, and it will not stop tomorrow night or the night after that, as long as there are people on this planet willing to step outside and turn their faces toward the dark. The universe puts on a show whether we are watching or not, but it means more when we watch. It means more when we understand what we are looking at, when we know that the thin crescent of the moon is glowing partly with light that bounced off our own planet, when we know that Venus is a world of crushing heat and acid clouds that somehow ended up as our nearest neighbour, when we know that the hazy smear of the Pleiades contains thousands of stars in dozens of different sizes and temperatures and life stages, all of them burning, some of them briefly and brilliantly, and some of them slowly and patiently across timescales the human mind can barely encompass. That knowledge does not push the beauty away. It makes the beauty larger. It makes the sky bigger and stranger and more wonderful than the sky of pure ignorance could ever be. On April 29th, NASA highlighted an alignment. Astronomers announced a discovery. People looked up, and the Pleiades, as they have done for every generation of humans who ever watched them cross the sky, were exactly where they were supposed to be, waiting for us to notice, waiting for us to look more closely, patient and ancient and full of secrets we're only now beginning to find. What makes a sky event like the one on April 29th linger in the memory is not just the visual, it is the accumulation of questions it plants in you afterward. You go back inside, you make tea, you lie awake, and you find yourself thinking about things you had not thought about since a middle school science class, or perhaps ever. Why does the moon have earthshine? How does a star cluster form in the first place? What does it actually mean to say that light left the Pleiades 440 years ago? What was happening on Earth in that moment, when those particular photons began their long journey toward your retinas? The answer to that last question is 1585, roughly. That is when the light reaching your eyes on a clear April evening actually departed the Pleiades. Shakespeare was 21 years old and had not yet written a single play. The Spanish Armada had not yet sailed. Galileo was a 21-year-old student with no particular reputation. The telescope did not exist. Nobody on Earth, looking up at the Pleiades on a clear night in 1585, had any idea what those stars were made of, how far away they were, or that centuries later their light would land on the eyes of a species that had, in the intervening time, developed instruments capable of counting thousands of previously invisible members of the cluster they were watching. That is what 440 light-years means in human terms. Not just a number, a timestamp. And if you want to take that game further, you can. The most distant stars in the Pleiades that the newest surveys have catalogued, the faint ones at the edges of the cluster's halo, sit somewhat farther away than the bright central stars, some of them perhaps 460 or 470 light-years out. The light from those stars arriving in your eye on April 29th left them when Copernicus's revolutionary model of the solar system was still brand new, still controversial, still being argued over by theologians and natural philosophers across Europe. The light that revealed those newly catalogued faint stars to modern instruments left them before anyone alive on Earth understood that Earth itself moves. There is something almost dizzying about that, if you let yourself sit with it. The universe has been sending us signals the entire time. We just had not yet built the ears to hear them. This is worth dwelling on because it gets at something fundamental about how our understanding of the cosmos has grown, and it sets up the next part of this story in a way that matters. Because the discovery of thousands of hidden stars in the Pleiades is not an isolated surprise. It is part of a pattern. It is the latest chapter in a very long story of the sky, revealing more than we expected every time we looked at it more carefully. Go back to the beginning of serious telescopic astronomy, the period when scientists first began systematically cataloguing the night sky, rather than just observing it for navigation or religious purposes. In that era, the Milky Way was understood to be a smear of light, a band across the sky, but nobody knew it was a galaxy. Nobody knew what a galaxy was. The stars visible to the naked eye were understood to be stars, but their distances were not known, their nature was debated, and the question of whether there were other systems of stars beyond our own was considered almost metaphysical, the kind of thing that could not be resolved by observation. Then the telescopes got better, and the more powerful they got, the more the sky refused to stay simple. Charles Messier, an 18th century French astronomer whose primary interest was actually comet hunting, kept making notes about fuzzy objects in the sky that he needed to catalogue so he would not mistake them for comets. His list of these annoying not comets became one of the most important documents in astronomical history. Messier objects, as we now call them, include galaxies, nebulae, and star clusters, many of them among the most beautiful and scientifically interesting objects in the sky. The Pleiades is a Messier object. So is the Great Nebula in Orion, where stars are forming right now, this moment, as you read this. So is the Andromeda Galaxy, the nearest large spiral galaxy to our own, which on a very dark night can be glimpsed with the naked eye as a faint smudge. Messier had no idea what most of these objects were. He was listing them as nuisances. He never imagined that his catalogue of things that are not comets would one day be treasured by astronomers worldwide as a kind of starter kit for understanding the structure of the universe. That is the irony at the heart of so much scientific discovery. You set out to study one thing and stumble onto something completely different that turns out to be far more important. You build a tool to answer one question, and it answers a dozen others you had not thought to ask. You make a list of what you cannot explain, and the list becomes a roadmap. The pattern holds all the way up to the present day. The James Webb Space Telescope, launched at the end of 2021 and fully operational by 2022, was designed to study the early universe, to look back toward the beginning of cosmic time and observe the first galaxies forming, and it has done that spectacularly. It has photographed galaxies so distant that their light left them less than 1 billion years after the Big Bang, when the universe was a fraction of its current age. But in the process of doing that work, it has also looked at nearby objects, at star-forming regions, at exoplanet atmospheres, at structures in our own galaxy, and in every case it has found more than the scientists expected. More stars, more complexity, more chemistry, more variety, more strangeness. The Webb telescope has the ability to see in infrared light, wavelengths longer than visible light that the human eye cannot detect at all. In the infrared, objects that are cool or dusty or far away and redshifted, stretched in wavelength by the expansion of the universe, become visible in ways they simply are not in ordinary visible light. This is why Webb can see the first galaxies. Their light has been redshifted so dramatically by 13 billion years of cosmic expansion that it arrives at Earth in infrared wavelengths that previous telescopes were not built to collect. But infrared vision also does something else. It sees through dust. And in astronomy, dust is everywhere. It fills the spaces between stars. It surrounds young stars as they form. It wraps around entire star-forming regions and obscures them in clouds of microscopic particles that block visible light, the way fog blocks headlights. Optical telescopes, telescopes that collect visible light, see the edges of these dusty regions and deduce what might be inside. Infrared telescopes see through the dust and observe the interior directly. This is part of why the surveys of the Pleiades have been turning up stars that older surveys missed. Some of those faint, low-mass stars are embedded in regions of the cluster that are dustier than average, regions where older observations in visible light were picking up the glow of the surrounding material, rather than the individual stars within. With infrared sensitive instruments, you can push through that dust and count what is actually there. And what is actually there, it turns out, is a lot more than the visible light was telling us. The practical implications of finding thousands of previously unknown cluster members go beyond simply correcting a count in a textbook. Knowing the true population of a star cluster changes our understanding of how star clusters form and evolve, which in turn has implications for how we understand galaxy formation as a whole, since galaxies are built partly through the merging and dispersal of star clusters over billions of years. Here is the key issue. When a cloud of gas and dust collapses to form a star cluster, it does not produce equal numbers of stars at every mass. It produces far more small, low-mass stars than large, high-mass ones. This relationship, called the initial mass function, is one of the most fundamental patterns in stellar astrophysics, and it appears to hold across a wide range of environments and conditions. For every massive, bright, hot star in a cluster, there are many more small, cool, dim ones. But if we were systematically missing thousands of those small stars in the Pleiades because our instruments were not sensitive enough to detect them, then our empirical verification of the initial mass function in this particular cluster was incomplete. The ratio of small to large stars that we thought we were measuring was a ratio calculated with incomplete data. Now, with a more complete census, we can test whether the Pleiades cluster actually does follow the expected pattern, and if it deviates, understanding why that deviation exists tells us something about the specific conditions under which this cluster formed. Early indications from the new surveys suggest that the Pleiades may have an unusual abundance of brown dwarfs, those almost stars that never quite ignited full nuclear fusion, relative to what the standard initial mass function would predict. If confirmed, that would be a significant finding, pointing towards something particular about the conditions in the molecular cloud that gave birth to the Pleiades roughly 100 million years ago. Perhaps the cloud was unusually cold or unusually dense in certain regions, creating conditions that favoured the formation of small objects over large ones. Perhaps there were specific physical processes at work that we do not yet fully understand. Or perhaps the discovery is telling us that our standard models of star cluster formation are missing something important. That is always a possibility in science. The model is built on what we have measured, and if what we have measured was systematically incomplete, the model is built on a foundation that was never quite as solid as we thought. This is not a crisis for astronomy. It is an opportunity. Every time the data outstrips the model, you have a chance to learn something new. The model either gets refined or it gets replaced by a better one. Either way, the understanding improves. But let us step back from the technical details for a moment, because there is another dimension to this story that I think deserves its own space to breathe. The Pleiades has been part of human consciousness for a remarkably long time, and that history is not just decorative, not just a pretty cultural backdrop to the real science. The cultural history of the Pleiades is itself a kind of scientific document, a record of how our species has engaged with the sky across tens of thousands of years, and it contains information that modern astronomers have actually found useful. Consider the question of how old the rock art at Lascaux actually is, and whether the Pleiades depicted there were accurate to the sky, as it would have appeared at the time of the painting. This turns out to be a serious question with a real scientific answer, because the sky does not look quite the same today as it looked 17,000 years ago. The Earth wobbles on its axis in a slow cycle that takes about 26,000 years to complete, a phenomenon called precession. Over time, this wobble shifts which stars are overhead at a given time of year, and it shifts the position of the celestial poles, the points in the sky that the Earth's rotational axis points toward. Today, the north pole of the sky lies near a star called Polaris, which is why Polaris is called the North Star. It sits close to the point the Earth's axis points toward, so it barely moves through the night while all other stars appear to wheel around it. But 17,000 years ago, the Earth's axis pointed toward a different part of the sky entirely, toward a region between the constellations we now call Hercules and Draco. The star that served as North Star for the cave painters of Lascaux was not Polaris. It was a star called Thuban, dim enough that most people today have never heard of it. When you account for this precession, the sky as it appeared above southern France 17,000 years ago looks a bit different from the sky above southern France tonight. And researchers who have carefully analysed the Lascaux cave paintings have found that the positions of the depicted stars match the sky as it would have appeared in that ancient era, not the sky as it appears now. This suggests that the artists were not just drawing symbols, they were drawing actual observations, actual positions of actual stars as they appeared in actual seasons at an actual historical moment. The cave at Lascaux may contain the oldest accurate astronomical record in human history, and the Pleiades, that same cluster that dazzled people on April 29th, appear to be part of it. There is a famous section of the Lascaux Cave known as the Hall of the Bulls, named for its large depictions of aurochs and bison. Among the images there, above the shoulder of a painted bull, is a cluster of dots, 6 to 7 dots, arranged in a pattern that matches the arrangement of the naked-eye stars of the Pleiades with considerable accuracy. Researchers have proposed that this image is not just decorative, but represents a specific moment in the sky, the moment when the bull in the sky, which we now call Taurus, appears near the Pleiades, which is exactly how the Pleiades sit in our modern sky, close to the shoulder of Taurus the bull, which is what makes Taurus a relevant constellation when we talk about the Pleiades' position. The ancient artists saw a bull in the sky with the Pleiades near its shoulder. They painted a bull on their cave wall with dots near its shoulder. Across 17,000 years of human history, through the rise and fall of every civilization, through ice ages and migrations and the invention of writing and mathematics and science, that image has persisted, recognizable, accurate, connecting us to observers who had no more sophisticated technology than firelight and patience and eyes just like ours. That is a profound kind of continuity, and it makes the April 29th alignment feel like something more than a pretty astronomical accident. It feels like a thread, one thread among thousands, connecting every generation of human skywatchers into a single ongoing conversation with the cosmos. There is another piece of the Pleiades' cultural history that tends to surprise people, and it involves a convergence that sounds almost too convenient to be real, but is very real. It concerns the Pleiades' role as an agricultural calendar, and it shows up independently in cultures separated by oceans and millennia. The Pleiades rise in the east in the evening sky in the northern hemisphere autumn. They are high overhead in winter, they set in the west in the evening sky in spring, and in summer they disappear entirely from the night sky, rising and setting during daylight hours when the sun outshines them. This annual cycle made them an obvious, visible, reliable calendar marker for anyone engaged in agriculture or pastoralism, anyone whose livelihood depended on knowing when to plant, when to harvest, when to move livestock to higher pastures, when to expect the rains. In ancient Greece, the evening rising of the Pleiades in the autumn marked the start of the sailing season. Their setting in the spring marked its end. Hesiod, writing around 700 BCE, advised farmers to begin their harvest when the Pleiades rose, to begin ploughing when they set, and to use their position to track the cycle of agricultural work through the year. The Pleiades were not just mythological figures for the Greeks. They were a practical instrument, a clock in the sky that everyone could read. In Japan, the cluster known as Subaru was used to regulate the agricultural calendar. In parts of West Africa, the Pleiades' appearance was used to time the planting of millet. Among the indigenous peoples of Australia, the Pleiades were associated with female ancestors, and their rising marked the season for certain ceremonies and food-gathering activities. Among the Lakota of North America, the cluster was associated with the Taurus constellation and carried ceremonial significance tied to the seasons. The pattern is so widespread that it raises a genuine question about cultural diffusion versus independent invention. Did the practice of using the Pleiades as a calendar spread from some single original culture outward across the world? Or did people in different places, observing the same sky, independently arrive at the same conclusion that this bright, distinctive cluster makes a useful anchor for tracking the year? The honest answer is that we do not know for certain, and likely different cultures arrived at the same practice through different routes. Some may have inherited it through ancient human migrations that carried astronomical knowledge alongside other cultural practices. Others may have figured it out independently, because the cluster is genuinely useful for this purpose, and the sky is the same sky everywhere. But what this convergence suggests is something important about the relationship between humans and the night sky. The Pleiades became a cultural touchstone not because of some random accident, but because the sky presents real, observable patterns that have real, practical consequences for human life. People paid attention to the sky because the sky mattered, because understanding its cycles was not a luxury or a pastime, but a survival skill. The mythology came later, the stories woven around the observations, but the observations came first, driven by necessity. And that brings us to something that connects the ancient Pleiades watchers to the scientists who announced the new star discovery in the same week as the April alignment, more directly than you might expect. Modern astronomy is, at its deepest level still in the business of pattern recognition. The instruments have changed, the mathematical frameworks have become extraordinarily sophisticated. The distances involved are unimaginably larger. But what astronomers do, fundamentally, is observe the sky, catalogue what they find, look for patterns, and try to understand what those patterns mean. The farmer in ancient Greece looking at the Pleiades to know when to harvest, and the astronomer running an infrared survey of the cluster to count its stellar population, are separated by 2.5 millennia of technological development. But they are engaged in the same basic enterprise: careful attention to the sky in the service of understanding the world. There is a beautiful irony in the fact that those thousands of newly discovered stars, the dim ones that recent surveys have been cataloguing, are exactly the kind of stars that ancient skywatchers could not see. Brown dwarfs emit almost no visible light. Low-mass red stars emit very little. The sky that the cave painters and the Greek farmers and the Maya calendar keepers were working with contained, to their eyes, only the bright stars, the ones that stood out against the dark well enough for unaided human vision to register. The population they were counting, and naming, and weaving into myth was only the brilliant surface layer of something vastly larger. They knew 6 or 7, we know 1,000, and now we are learning the 1,000 was itself an undercount, and the real number is somewhere in the thousands more. Each generation sees further than the last, not because we are smarter, not because we care more, but because we stand on the accumulated work of everyone who looked before us, and built a slightly better instrument and asked a slightly better question. Isaac Newton put it modestly when he said he stood on the shoulders of giants. What he may not have fully appreciated was how many of those giants were anonymous, how many of the observations his mathematics was explaining had been gathered by nameless farmers and sailors and shepherds and cave painters who tracked the sky for reasons entirely disconnected from the mathematical physics he was developing. The data flowed forward through time even when the people who gathered it had no idea it would eventually be used this way. The Pleiades count accumulated from 7 to 1,000 to thousands more across that long relay, and it will accumulate further. Future instruments will certainly find more. The universe, as a general rule, contains more than we think it does. Let us talk about the future of the Pleiades, because the cluster does have one, and it is stranger than most people realize. A star cluster is not a permanent fixture. Unlike the stars themselves, which can persist for billions or even trillions of years, clusters are fragile social structures, held together by the mutual gravity of their members, gradually pulled apart by the gravitational influences of passing molecular clouds, by the tidal forces of the galaxy as a whole, and by their own internal dynamics, the occasional close encounter between stars that sends one member hurtling away at high speed, slowly eroding the cluster's population. The Pleiades, at roughly 100 million years old, are still relatively youthful and cohesive. The cluster has not yet lost most of its members to dynamical evaporation, but the process is ongoing. Stars are gradually drifting away from the cluster, following their own paths through the galaxy, no longer gravitationally bound to their siblings. In another few 100 million years, the Pleiades as a recognizable cluster may be significantly disrupted, its members scattered across a larger volume of space, no longer appearing as a tight group in the sky. In 1 billion years, the bright blue stars that give the cluster its distinctive appearance will be gone. They will have burned through their fuel and died, either exploding as supernovae or, if they are at the lower end of the mass range, more quietly collapsing into white dwarfs. What remains will be the smaller, cooler stars, the ones that were largely invisible to human eyes for all of recorded history, the ones that new surveys are only now beginning to count in earnest. The Pleiades of the deep future, if anything remains cohesive enough to merit the name, will be a cluster of dim red stars and brown dwarfs, drifting apart, invisible to any future beings who might be watching from this part of the galaxy, assuming any are. The brilliant sisters we see tonight are ephemeral, in cosmic terms. 100 million years seems like an eternity to human beings, but it is a blink on the timescale of the universe. Our own solar system is 4.5 billion years old. The universe itself is nearly 14 billion years old. 100 million years is about 2% of Earth's current age. When you look at the Pleiades, you are looking at something in the early chapters of its story. Young, hot, bright, still organized, still identifiable, still announcing itself with that characteristic blue-white glow, something that will eventually dissolve into the general stellar population of the Milky Way, its sisters scattered to the galactic winds, unrecognizable as a family. But that dissolution is not a tragedy. It is what happens. The stars that drift away from the Pleiades will continue their own lives. Some of them may have planetary systems, and those planets, if they have not already been sterilized by the ultraviolet radiation from the cluster's hot stars, might eventually cool to conditions where liquid water could exist. The dispersing stars carry their worlds with them into the galaxy. What looks like dissolution is also a kind of dispersal, seeds scattered across space. And the Pleiades have already given the galaxy a gift that extends far beyond their own eventual dissolution. The massive stars in the cluster, when they die, will explode as supernovae. Each supernova is an event of almost incomprehensible violence and energy, a star destroying itself in a fraction of a second, releasing more energy than our Sun will emit in its entire 10 billion year lifetime. But supernovae are also generators. In the extreme conditions of those explosions, heavy elements are forged, atoms heavier than iron that cannot be produced by ordinary stellar fusion. These elements, everything from cobalt to gold to platinum to uranium, are blasted outward by the explosion, seeding the surrounding interstellar gas with materials that will eventually be incorporated into new stars, new planets, and potentially new living things. The iron in your blood was forged in the heart of a dying star. The calcium in your bones, the oxygen in every breath you take, every heavy element in your body was produced by nuclear processes inside a star and distributed into the galaxy by that star's death. You are, quite literally, made of ancient starfire. The Pleiades will add to this inheritance. When its massive stars die over the next few 100 million years, they will enrich the surrounding interstellar medium with the products of their short, brilliant lives. That enriched gas will eventually collapse into new stars and new planetary systems. Those systems will be slightly more chemically complex than the systems that formed from less enriched gas before them. The Pleiades are not just beautiful. They're contributing to the ongoing chemical evolution of the galaxy, nudging the cosmos, slightly but measurably, toward greater complexity. This is what astrophysicists mean when they talk about stellar evolution in a broader sense. Individual stars evolve, but so does the whole system they are embedded in. Stars are not isolated objects. They are nodes in a network, exchanging material and energy across vast distances and long timescales, each generation inheriting the chemical output of the previous one, each generation leaving something for the next. The Pleiades, ancient as they seem to us, are participating in that network. They have already begun giving back what they took from the interstellar medium when they formed, in the form of stellar winds and the energetic radiation that is gradually ionizing gas in the cluster's immediate vicinity. Their most massive members will eventually give back everything else in their final explosive moments. We are watching them in the middle of this process, in the brief window when they are bright and young and arranged in their beautiful familiar pattern. 440 years from now, when the light leaving the Pleiades tonight finally arrives, wherever the human story has taken us by then, the cluster will look very similar to how it looks tonight. The stellar timescales are simply too long for any human civilization to watch meaningful change in a single star cluster's life. We get a still frame. The motion is too slow for our eyes and our generations, but knowing that the motion is there, knowing that we are watching a process, a story, a community of stars living out their lives in slow motion, makes the still frame more interesting. You look up and see a snapshot and know that you are looking at something that has a past and will have a future, that you are positioned at one particular moment in a narrative that began before Earth existed and will continue long after it is gone. That is, again, what understanding adds to observation. Not complication, depth. Now there is a question that comes up often when people first encounter the scale of these distances and these timescales, and it is worth addressing directly because it touches on something genuinely unresolved in the science. The question is this: given how many stars there are, given how many of them are similar to our Sun, given how many of those have planetary systems, given how long the universe has been around, given that stars have been forming and planets have been forming, and chemistry has been happening for billions of years before our solar system even existed, why is the sky so quiet? This is the Fermi paradox, named for the physicist Enrico Fermi, who supposedly asked some version of it during a lunchtime conversation with colleagues in 1950. The logic is straightforward. If the universe is old and large and full of stars and planets, and if life arises wherever conditions permit, and if some fraction of that life eventually becomes technologically capable, then by now the galaxy should be full of civilizations. Some of them should have been around for billions of years longer than we have. Even at speeds far below the speed of light, a sufficiently old civilization could have colonized, or at least explored, a significant fraction of the galaxy by now. So where is everyone? The silence is puzzling. We have not detected any unambiguous signals of extraterrestrial intelligence. We have found no obvious signs of engineered structures in the sky. The galaxy appears, to our current instruments and our current level of searching, to be quiet in the ways that would indicate widespread technological activity. This does not mean the galaxy is lifeless. It does not even mean it is free of intelligent life. Our search has been limited and brief and focused on particular kinds of signals. We have been systematically looking for extraterrestrial intelligence for only a few decades, using techniques that assume other civilizations communicate in ways similar to how we communicate, using radio waves or optical lasers pointed in our direction. That is a set of assumptions that may or may not be valid. But the puzzle is real, and it has generated an enormous number of proposed solutions, each of which implies something different about the nature of life and intelligence in the universe. One class of solutions involves what are sometimes called filters. The idea is that there are obstacles, bottlenecks, critical thresholds that must be crossed for life to progress from simple chemistry to complex organisms to intelligent beings to technological civilization. These obstacles are not insurmountable because we exist, but they may be extremely rare to surmount. If any of these bottlenecks is rare enough, life might not make it through. The origin of life itself could be one such filter. Going from chemistry to self-replicating, metabolizing organisms is a step that we do not fully understand. It happened on Earth relatively quickly after conditions became suitable, within a few 100 million years of the planet's formation. But we do not know if that was inevitable given those conditions, or extraordinarily lucky. If it required a sequence of molecular accidents so improbable that it happens only once in every billion Earth-like planets per billion years, then complex life might be genuinely rare even in a universe with billions of Earth-like planets. The evolution of complex multicellular life could be another filter. Simple, single-celled organisms dominated Earth for nearly 3 billion years before complex multicellular life appeared. That transition may have required a specific combination of circumstances, including the evolution of the mitochondrion through a merger of two different types of single-celled organisms that are far from guaranteed. And intelligence itself, with all the complexity of nervous systems, social organization, language, and technological development, may be another rare threshold. The unsettling version of the filter hypothesis, sometimes called the Great Filter, is the possibility that the most difficult bottleneck lies not behind us, in the past, but ahead of us, in the future. If the filter is something that sophisticated technological civilizations typically encounter and fail to survive, a self-inflicted catastrophe of some kind, then the silence of the sky might be a warning rather than an invitation. But there are more optimistic resolutions to the puzzle as well. Perhaps technological civilizations are common, but they communicate in ways we have not thought to look for. Perhaps they evolved away from the kinds of radio communication we're searching for long before we would have been listening. Perhaps interstellar distances are genuinely prohibitive, even for advanced civilizations, limiting expansion and making the galaxy look empty even when it is not. Perhaps most intelligent life is simply not interested in making itself detectable across light years of space, and quiet civilizations leave no signature we know how to look for. The Pleiades are relevant here in a way that is not immediately obvious. Among the newly catalogued low-mass stars in the cluster, some of them are old enough and stable enough that, if they have planetary systems, those planets have had many tens of millions of years under relatively steady conditions to develop whatever chemistry they are going to develop. 100 million years is a long time. Earth was a very different place 100 million years ago, and it already had complex multicellular life by then. Dinosaurs were walking on it. Flowering plants were beginning to evolve. The oceans were full of organisms with hard shells and complex behaviors. The low-mass stars being discovered in the Pleiades are not sun-like stars. They are smaller and cooler, and the habitable zones around them, the distances at which liquid water could exist on a planet's surface, lie much closer in than Earth's distance from the Sun. But those habitable zones exist, and small, cool stars are the most common type in the galaxy. If life can take hold around them, The universe is far more likely to be inhabited than if life requires conditions like those on Earth around a sun-like star. We do not know whether life exists around any star in the Pleiades. We do not have the capability yet to detect biosignatures at that distance. The cluster is close on the cosmic scale, but still extraordinarily far for the current generation of instruments to probe for the chemistry of life on distant worlds. But the question is no longer idle speculation. It is a question that future telescopes will be capable of beginning to address, at least for the nearer star systems, and the census of what is out there, the count of stars and their likely planetary companions, is a prerequisite for knowing where to look. Every new star catalogued in the Pleiades is, among other things, a new candidate host for worlds we have not discovered yet. Every additional member of the cluster's population is another point on the map of potential places where the experiment of life might be running. That is perhaps the most exciting reason to care about a discovery that might otherwise sound like a fairly dry astronomical correction. We thought there were 1,000 stars. There are considerably more. Some of those additional stars, the cool, stable, long-lived ones, might have planets. Those planets might have conditions suitable for chemistry. That chemistry might, over millions of years, produce something interesting. We do not know. We cannot yet check. But we have, in the act of counting more carefully, expanded the list of places where the question is even worth asking. That is always how science works in its most exploratory mode. You survey the territory, you map what is there, you build the inventory, and then, with that inventory in hand, you start asking which items on the list deserve closer attention, which might reward further study, which contain something you have not yet found but have good reason to look for. The Pleiades survey is that kind of work, patient, systematic, designed not to answer a particular question but to establish the facts on the ground, or in this case the facts in the sky, comprehensively enough that better questions can be formulated afterward. Let us come at this from a different angle now, because there is a dimension of the April 29th alignment that we have not yet fully explored, and it connects to something that tends to genuinely surprise people when they first encounter it. The crescent moon that hung in the sky that evening was not just a crescent. As the original account noted, the dark portion of the moon's disk was faintly visible, glowing with a soft, ghostly light. This phenomenon, earthshine, is one of the most quietly remarkable things you can observe with the naked eye, and the physics behind it is a beautiful closed loop of illumination that few people ever stop to think about. Here is what is happening when you see earthshine. The sun is illuminating Earth. Earth is reflecting some fraction of that sunlight into space in all directions, including toward the moon. The moon, a roughly spherical body with a rocky, somewhat reflective surface, bounces some of that Earth-reflected light back toward Earth, and your eyes, standing on the surface of Earth, receive that twice-reflected light and perceive it as a faint illumination on the part of the moon that the sun's direct light is not currently reaching. The sunlight takes a round trip, sun to Earth, Earth to moon, moon to Earth. 3 legs of a journey, and at the end of it, your eyes are gathering photons that have travelled that whole circuit and preserved information about the reflection properties of Earth's surface. This is not just aesthetically interesting, it is scientifically useful, and for a rather striking reason. The earthshine you see on the moon is carrying information about what Earth looks like from space, which parts of it are covered by clouds on that particular day, which parts are ocean, and which are land, how reflective each surface type is. By studying earthshine, astronomers can actually measure how the reflectivity of Earth's surface, what scientists call albedo, changes over time, and those measurements show something that matters. Earth's albedo has been decreasing over recent decades. Earth is reflecting less sunlight back into space than it used to. Some of this is cloud pattern changes, which are complex and not fully understood. Some of it is connected to melting ice, because ice is highly reflective and open ocean is not, and as Arctic sea ice retreats, the overall reflectivity of Earth's surface decreases. When you look at earthshine on the crescent moon and appreciate how lovely it is, you're also, if you know what you're looking at, receiving a report on the state of Earth's climate. The ghost of sunlight on the dark moon is a thermometer, a mirror that shows you what your planet looks like from outside. Every component of the April 29th alignment, it turns out, has layers like this. The surface is beautiful. Pull back the surface and you find science. Pull back the science and you find implications. Pull back the implications and you find connections to things that matter directly to the lives of the people who are standing in their backyards taking photographs. The Moon is measuring Earth's reflectivity. Venus is demonstrating what happens to a rocky world when a runaway greenhouse effect heats it past the point of no return. The Pleiades are telling us how star clusters form and populate themselves, how many more stars exist in familiar places than we thought, how the galaxy enriches itself chemically across billions of years, and all of it is visible, or nearly visible, on a clear evening with patience and the right piece of knowledge to know what you are seeing. This is what astronomical education is actually trying to do when it is done well. Not to replace the experience of looking at the sky with a stream of facts that make the beauty feel clinical, but to enrich the looking, to add depth and resonance to what is already beautiful, to give people the tools to see more than their unaided eyes can show them. A person who knows nothing about the Pleiades and looks at them on a clear night sees a pretty smudge of stars. A person who knows a little about them sees the mythological sisters, the Japanese car logo, the cave paintings. A person who knows more sees the distance, the age of the light, the temperature and colour of the individual stars. A person who knows still more sees the new census, the thousands of hidden low-mass stars, the brown dwarfs, the initial mass function, the 100 million-year history of the cluster's formation, and the future of its dissolution. A person who knows about the April alignment sees all of that plus the orbital mechanics that brought Venus and the Moon into the same small patch of sky, plus the history of how ancient cultures tracked those same objects and wove them into their understanding of time and agriculture and ceremony. The sky gets richer the more you know about it. The beauty compounds. There is never a moment when more knowledge makes it less. There is always a deeper layer to find. Now we have to talk about Venus more seriously, because Venus deserves more than supporting actor status in this story. It blazed in the April sky with a brilliance that photographs struggle to capture without overexposing everything around it, and the reason for that brilliance is a story of its own, one that connects to some of the most active and important research happening in planetary science right now. Venus is, by almost any measure, the most extreme planet in our solar system. Not in terms of size or distance or magnetic fields, but in terms of the gap between its physical reality and what you might naively expect from a planet in its position. Start with the basics. Venus is nearly the same size as Earth, nearly the same density, nearly the same gravitational pull. If you were designing a solar system and wanted to create an Earth-like world, you would be hard-pressed to produce something more physically similar to Earth than Venus. It orbits slightly closer to the Sun, but not dramatically so. For a brief period in the history of planetary science, some researchers speculated that Venus might be a tropical world, perhaps covered in swampy vegetation under its thick, opaque cloud cover, a sister world warm and lush rather than hostile. The reality, when spacecraft finally pierced that cloud cover and measured conditions on the surface and in the atmosphere, was catastrophic in the most literal sense. Venus's surface temperature sits at around 465 degrees Celsius. That is not just hot in the way that a desert is hot or a fire is hot. That is hot enough to melt lead, hot enough to glow faintly in the dark if you could somehow observe it in an unlit room, hot enough to destroy virtually every material we use in spacecraft construction within minutes of exposure. The Soviet Venera probes, which successfully landed on Venus's surface in the 1970s and 1980s, were extraordinary engineering achievements precisely because they managed to survive long enough to transmit data, with the most successful ones lasting just over 2 hours before the crushing heat and pressure destroyed them. And the pressure is its own story. At Venus's surface, the atmospheric pressure is about 90 times what we experience on Earth at sea level. This is roughly equivalent to the pressure you would experience diving nearly a kilometre below the surface of the ocean. Every square centimetre of your skin, if you were somehow standing on Venus's surface, would be experiencing the weight of a column of atmosphere extending 70 kilometres above you. That thick atmosphere is mostly carbon dioxide with clouds of sulfuric acid. The carbon dioxide creates an extreme greenhouse effect, trapping heat from the sun far more efficiently than Earth's more dilute carbon. Dioxide atmosphere traps heat here. The result is that Venus, despite being somewhat farther from the sun than Mercury, is actually hotter than Mercury at the surface. The greenhouse effect is so powerful that it overwhelms the distance factor entirely. What makes Venus particularly interesting from a planetary science perspective is that it almost certainly was not always like this. The best current models of planetary formation and early solar system history suggest that Venus, early in its life, may have had liquid water on its surface. It may have had a global ocean. It may have had a climate not entirely unlike early Earth's. At some point this changed. The precise mechanism and timing are still debated, but the general picture is that as the Sun gradually brightened over the first 1 billion or 2 years of the solar system, Venus's relatively modest initial water supply began to evaporate. More water vapour in the atmosphere created a stronger greenhouse effect, which raised temperatures, which evaporated more water, which strengthened the greenhouse effect further. This is what planetary scientists call a runaway greenhouse, a feedback loop that amplifies itself until all the water is gone, baked into the upper atmosphere where ultraviolet radiation from the Sun breaks it apart, and hydrogen escapes into space, while oxygen either escapes or gets chemically incorporated into rocks. Once the water is gone, Venus is locked into its current hell. Without water cycling through the system, the mechanisms that remove carbon dioxide from Earth's atmosphere, most notably the weathering of rocks and the incorporation of carbon into carbonate minerals that eventually get subducted into the mantle, no longer operate effectively. Carbon dioxide builds up from volcanic outgassing, accumulates in the atmosphere, and the greenhouse effect strengthens further. The planet bakes itself. The chilling implication is that this process does not require extraordinary circumstances. It did not happen to Venus because Venus was particularly unlucky or particularly unusual. It happened because Venus was just slightly closer to the Sun than the margin of safety allowed, and that slight proximity, combined with the Sun's gradual brightening over time, tipped the balance. The transition from potentially habitable to unambiguously hellish may have taken only a few 100 million years. On the timescale of planetary history, that is fast. This is why Venus matters so much to the scientists who study climate, and to the scientists who study planetary habitability, and ultimately to the scientists who study Earth. Venus is not a cautionary tale from science fiction. It is a data point, the only nearby example of a rocky planet that underwent a runaway greenhouse transition. Understanding exactly how and when Venus became what it is, what conditions triggered the transition, how quickly it proceeded, and what physical fingerprints it left behind, is directly relevant to understanding the conditions under which Earth could potentially follow a similar trajectory on whatever timescale. That timeline, and the factors that would accelerate or decelerate it, is something that planetary scientists care about deeply, and that climate modelers use as a comparison case for understanding the sensitivity of planetary atmospheres to greenhouse forcing. Venus does not threaten us imminently. Earth's situation is different in important ways, including our distance from the Sun, our water abundance, and the operation of geochemical feedback cycles that help stabilize Earth's temperature. But Venus shows that rocky worlds similar in size and composition to Earth are not guaranteed to be habitable. The margin can be narrow, the transition can be triggered. There is a currently active mission dedicated to studying Venus in a way that will dramatically improve our understanding of exactly these questions. The mission was conceived partly to answer the question of whether Venus ever had liquid water, to try to find geological evidence of an ancient ocean in the rocks and structures of Venus's surface, to look for minerals that could only form in the presence of liquid water, to search for the preserved remnants of ancient shorelines or sedimentary deposits. If such evidence is found, it will confirm that Venus was once habitable and then lost habitability, transforming our understanding of the solar system's history and of the fragility of habitable worlds. If no such evidence is found, it may mean that Venus was never habitable, that its slightly closer proximity to the Sun kept it just above the threshold for liquid water even in its earliest, coolest period, which would have its own interesting implications for where exactly the inner edge of the habitable zone lies around a Sun-like star. Either answer would be enormously valuable. The question is one of the most important unanswered questions in planetary science, and it is answerable, in principle, with the right observations from the right platform in the right orbit around Venus. Meanwhile, Venus's atmosphere has thrown up its own mystery that has generated considerable controversy and considerable scientific excitement over the past several years. In 2020, a team of researchers announced that they had detected a compound called phosphine in Venus's cloud layers. Phosphine is a molecule consisting of one phosphorus atom bonded to 3 hydrogen atoms. On Earth, phosphine is associated with biological processes. It is produced by certain microbes in oxygen-depleted environments, in swamps and marshes in the intestines of animals. Its presence in an atmosphere under conditions where it should be rapidly destroyed by sunlight is, on Earth, considered a potential biosignature, a chemical signature whose most plausible explanation involves biological activity. The detection in Venus's atmosphere was immediately controversial. Critics pointed out that the measurement was difficult, and that potential contamination or instrumental artifacts might explain the signal. Several subsequent analyses questioned the original data reduction, and follow-up observations struggled to confirm the original detection at the same level of significance. The controversy has not been resolved. The data is genuinely ambiguous. Different research groups analysing the same observations have reached different conclusions about whether the phosphine signal is real and at what concentration, if real, the compound is present. This is normal for a scientifically challenging measurement at the boundary of instrumental capability. The question will not be settled by argument over existing data. It will be settled by better observations, by dedicated instruments specifically designed to look for phosphine and other potential biosignature compounds in Venus's atmosphere, at a level of sensitivity sufficient to either confirm a robust signal or place an upper limit that rules out the original claim detection. What makes the phosphine story interesting is not the claim itself, which may or may not hold up, but what it represents. Scientists were sufficiently willing to take Venus seriously as a potential site of biological activity to conduct this kind of search, and to publish a result that they knew would attract both enormous interest and enormous skepticism. The cloud layers of Venus sit at an altitude where temperatures and pressures are actually relatively moderate, far more survivable than the surface. At around 50 kilometers above the surface, temperatures are in the range of 0 to 50 degrees Celsius, and pressures are similar to Earth's surface. In those conditions, extreme by Earth standards but not entirely outside the range of what some bacteria tolerate, could microbial life exist? The question sounds absurd for a planet as hostile as Venus. But the cloud layers are where the sun's energy is most available, where water vapor is more concentrated than anywhere else in Venus's atmosphere, and where certain chemical reactions are occurring that remain partially unexplained by purely abiotic chemistry. The hypothesis is not mainstream, but it is not dismissed either. It is the kind of idea that the scientific community treats with appropriate skepticism while keeping the door open, because the cost of being wrong in the direction of too much skepticism, of prematurely dismissing a genuine discovery, is enormous. The universe has surprised us before, it will surprise us again. The right response to surprising claims is not reflexive dismissal, it is rigor. There is something poignant about Venus in this context. Here is the planet that ancient peoples called the evening star and the morning star, that inspired more direct mythological attention than perhaps any other object in the sky aside from the sun and moon, that dazzled observers in every culture, that sailors used to navigate and farmers used to time their planting and priests used to anchor their ritual calendars. Ancient Babylonian astronomers compiled detailed records of Venus's movements over decades. The Maya built entire architectural features oriented to observe Venus's rising at key moments in its cycle. The ancient Greeks believed the evening star and the morning star were two different objects before Pythagoras, or someone in his school, deduced that they were the same thing. All of that attention, all of that observation, all of that mythological weight for a planet that turned out to be one of the most hostile environments in the solar system, a crushing, searing, acid-clouded hell that destroys spacecraft in minutes, and that may, possibly, harbour microbial life drifting in its temperate upper cloud layers because the surface is simply too awful to live anywhere else. That contrast is very Venus. Beautiful from a distance, lethal up close, possibly not entirely lifeless despite everything. Strange enough to keep scientists arguing about it for decades. And it was there on April 29th, blazing in the western sky like a beacon, one of the anchors of a celestial alignment that sent people rushing for their cameras. Let us shift our attention to something that the alignment story gestures toward, but does not fully develop, which is the remarkable amount we have learned about the stars of the Pleiades cluster at a chemical level, because that chemistry tells a story about the broader history of the galaxy in a way that illuminates everything we have been discussing. Stars are not made of the same stuff as each other. They are mostly hydrogen and helium. Yes, that is true of essentially all stars in the universe. But the trace elements, the elements heavier than hydrogen and helium, that astronomers lump together under the term metals, regardless of whether they are actually metallic by any other definition, vary significantly from star to star and cluster to cluster, and that variation is a fossil record of the galaxy's history, written in atomic abundances rather than rock layers. The very first stars that formed in the universe, shortly after the Big Bang, were made almost entirely of hydrogen and helium. There were essentially no heavier elements, because heavy elements are produced inside stars through nuclear fusion and distributed into the interstellar medium when those stars die. The first generation of stars, having no stellar predecessors to inherit heavy elements from, were chemically pristine by the standards of later generations. As successive generations of stars have formed, burned, and died, the interstellar medium has been progressively enriched with the heavy elements those stars produced. Each new generation of stars forms from material that contains slightly more heavy elements than the generation before it. Astronomers measure this enrichment using what they call metallicity, the ratio of heavy elements to hydrogen in a star's atmosphere. High metallicity indicates a star formed from gas that had already been processed through multiple previous generations of stars. Low metallicity indicates a star from an earlier, less enriched era. The Pleiades stars have metallicity roughly similar to the Sun, slightly higher in some measurements, slightly lower in others, consistent with their roughly similar age and formation environment within the Milky Way disk. This tells us that the molecular cloud that gave birth to the Pleiades 100 million years ago was already well enriched, already carrying the chemical legacy of billions of years of stellar births and deaths before it. But what about the chemical composition in more detail? Astronomers have been able to measure, star by star in the Pleiades, the abundances of many individual elements: oxygen, carbon, silicon, iron, calcium, magnesium, nickel, and others. These detailed abundance patterns serve as chemical fingerprints, and they contain information about exactly which types of previous stars, in what proportions, contributed their material to the molecular cloud that formed the Pleiades. When you see an excess of oxygen relative to iron, for example, it suggests that the gas in your formation environment was enriched primarily by massive stars that explode as a particular type of supernova, because that type of supernova produces large amounts of oxygen but relatively little iron. When you see a high ratio of iron relative to lighter elements, it points to contributions from a different class of stellar explosions, the thermonuclear detonations of white dwarf stars in binary systems, which are efficient producers of iron and nickel. The Pleiades' detailed chemical abundances have been analysed and cross-referenced with models of galactic chemical evolution, and what emerges is a picture consistent with formation from a gas cloud that was a typical product of Milky Way disk evolution, reflecting the accumulated output of billions of years of stellar generations spread across the galaxy's history. There is nothing dramatically unusual in the Pleiades' chemistry. They are not a chemical oddity. They are, in some sense, a representative sample of what the Milky Way's star-forming material looked like 100 million years ago in our part of the galaxy. But representative does not mean boring. Representative means connected. Connected to everything that came before, to every star that ever lived and died in this part of the galaxy, and contributed its matter back to the reservoir from which new stars could form. When you look at the Pleiades, you are looking at a cluster built from the ashes of stars that are now long dead, stars that burned their lives out before Earth existed, before our Sun had even formed. The Pleiades are built, chemically, from a history that predates them by billions of years, and every star in the Pleiades is itself contributing to that reservoir through the stellar winds that blow off their outer layers and the eventual explosive deaths of the most massive members. The galaxy's chemical enrichment process is ongoing. The Pleiades are not just recipients of the galaxy's history, they are contributors to its future. This is the deep structure of everything, cycles of matter and energy operating on timescales and scales far beyond anything humans can directly experience, but accessible to us through the patient work of observation and analysis, through the act of pointing instruments at the sky and asking what the numbers mean. The newly catalogued low-mass stars in the Pleiades, those thousands of previously invisible members, are participating in this cycle too in their quiet way. Brown dwarfs, at the low end of the newly discovered population, are barely losing any mass at all, holding their material tightly through their long, slow lifetimes. But they are there, gravitationally part of the cluster, contributing to its total mass and its dynamical behaviour, part of the full accounting of what the Pleiades actually are. Getting that accounting right, knowing the full population rather than just the bright and visible fraction, is not merely an exercise in bookkeeping. It changes our understanding of the cluster's mass, its gravitational binding energy, how long it will remain coherent before dispersing, how its dynamics will evolve as the massive stars die, and the gravitational balance shifts. The full picture is different from the partial picture in ways that matter. This brings us, in a somewhat roundabout way, to a broader point about completeness in science. One of the most persistent challenges in every scientific field is the problem of what is sometimes called selection bias or detection bias. You can only study what you can detect, and the things you can detect are systematically different from the full population of things that exist. In astronomy, this problem is pervasive and deeply ingrained. The brightest stars are easiest to see, so historically we knew the most about them, and were tempted to build models based on them that may not represent typical stars at all. The nearest galaxies were the first to be studied in detail, and they may not be representative of the broader galaxy population. The most dramatic energetic phenomena, the supernovae, the gamma-ray bursts, the quasars, attracted the most attention early in the history of observational astrophysics, but they represent the exceptional rather than the normal. Every time astronomers manage to push their instruments to greater sensitivity, to deeper surveys, to longer observations, they find that the underlying population of objects is different from what the brightest, most easily detected members suggested. There are more faint galaxies than bright ones. There are more small stars than large ones. There are more subtle, quiet phenomena than spectacular ones. The universe's ordinary business is conducted by objects that are easy to miss, not by the show-offs that announce themselves to every passing telescope. The Pleiades survey is a beautiful example of this principle. The visible surface of the cluster, the stars bright enough for ancient peoples to name and modern visual observers to count, was misleading us about the cluster's true nature. The true nature, revealed by patient, sensitive survey work, is far richer and more complex than the visible surface suggested. If this principle applies in the Pleiades, it applies everywhere. Every object we think we understand well enough to stop looking at carefully is probably hiding something. Every population we think we have counted is probably undercounted by some factor that we will not know until we build better instruments and look again. That is not a counsel of despair, it is an invitation. The universe is more interesting than what we can currently see of it. The next instrument will show us more than the current one. The next survey will find things the current one missed. Science is not converging on a final answer. It is a process of continuously expanding what we know, and in doing so, continuously expanding the boundary of what we realize we do not yet know. The Pleiades, sitting 440 light-years away in a patch of sky where Moon and Venus came to visit on a beautiful April evening, are still revealing new things to us after 100,000 years of human observation. The cave painters scratched them into stone, the ancient Greeks named them, medieval navigators steered by them, modern astronomers photograph them and catalogue their members and build models of their formation and evolution. And the cluster, patient and ancient and full of more members than we knew, continues to yield new information to anyone willing to look carefully enough. There is something almost personal about that. The sky is not passive. It does not simply sit there displaying itself and waiting for us to be impressed. It waits for us to ask better questions, to build better instruments, to develop better frameworks for interpretation, and then it answers those questions with information it has been encoding in light for hundreds of millions of years. It was always sending the signal. We have been gradually learning how to receive it. Let us go somewhere that seems at first like a significant departure from our main story, but turns out, as these things often do in astronomy, to loop back in ways that illuminate everything we have been discussing. On the same timescale that the Pleiades have existed as a recognizable cluster, on the timescale of roughly 100 million years, something else has been happening in our galaxy that connects directly to why we can see the Pleiades at all, why Earth is in a position to have observers on it who can look up, and why the story of a life in the cosmos is more intertwined with the story of stellar physics than most people appreciate. Our Sun is not a lone wanderer through the galaxy. It is part of a massive structure, the Milky Way, a barred spiral galaxy containing between 100 and 400 billion stars, depending on how you count and what counts as a star, and we are embedded within one of its spiral arms, at a distance from the galactic center that puts us in what astronomers sometimes call the galactic habitable zone. The concept of a galactic habitable zone works by analogy with the planetary habitable zone. the range of distances from a star where liquid water can exist on a planetary surface. The galactic habitable zone is the range of distances from the galactic centre where conditions are thought to be reasonably conducive to the development of complex life, not too close to the centre where stellar density and radiation levels are extreme and gravitational dynamics are chaotic, and not too far from the centre where the abundance of heavy elements in the interstellar medium becomes too low to form rocky planets with the chemical complexity that life, as we understand it, requires. Our solar system sits at a comfortable distance from the galactic centre, roughly halfway out from centre to edge, in a position that is thought to be relatively stable, relatively metal-rich compared to the outer galaxy, and relatively free from the most violent energetic processes that make the inner galaxy so hazardous. The Pleiades are in a similar part of the galaxy, close to us in galactic terms, formed from material chemically similar to the material that formed our solar system, embedded in the same general neighbourhood of the Milky Way's disk. This means that the conditions that made it possible for life to develop on Earth, the chemical composition, the relative stability of the galactic environment, the availability of heavy elements, are roughly the same conditions that prevail in the Pleiades and its newly discovered population of low-mass stars. This is not a trivial point. It means that those newly catalogued dim stars in the Pleiades are not alien environments in the way that stars in the galactic centre, or stars in very metal-poor ancient globular clusters, would be alien. They formed from chemically similar raw material. If some of them have planets, those planets may have formed from material similar in broad composition to the material from which Earth and the other rocky planets of our solar system formed. The factor that might make them most different from the solar system is precisely what makes them interesting from an astrobiological standpoint. Most of the newly discovered stars in the Pleiades are low-mass, cooler stars, and the research on whether such stars are good hosts for habitable worlds is some of the most active and rapidly evolving work in modern planetary science. The immediate concern with small, cool stars as hosts for habitable planets is a phenomenon called tidal locking. When a planet orbits close enough to its star, which it must in order to be warm enough to maintain liquid water, given the star's lower luminosity, the gravitational interaction between the star and the planet can synchronize the planet's rotation period with its orbital period. The planet ends up always showing the same face to its star, the way the moon always shows the same face to Earth. One side would be in permanent daylight, the other in permanent night. For a long time, this was considered potentially fatal for habitability. The day side might be scorched by intense, unending sunlight. The night side might be frozen in perpetual darkness. The temperature gradient between the two hemispheres might drive atmospheric circulation so extreme that life would be impossible to sustain. But more recent modelling has complicated this picture considerably. Some simulations suggest that tidally locked planets around small, cool stars could actually maintain relatively stable climates through atmospheric circulation patterns that transport heat from the day side to the night side effectively enough to prevent the most extreme temperature differentials. The presence of an ocean would help enormously, as water has a very high heat capacity and would resist temperature extremes in the night side regions where it might otherwise freeze completely. Other simulations show that some configurations of tidally locked planets can maintain liquid water on a meaningful fraction of their surface area, concentrated in a ring around the terminator, the boundary between perpetual day and perpetual night, where temperatures and lighting conditions might be intermediate and relatively stable. The other major concern with small, cool stars as hosts for habitable planets is their tendency to produce powerful flares. These stars are often magnetically active, particularly when young, and they generate violent outbursts of energetic radiation and charged particles that could, in principle, strip away a planet's atmosphere over time or deliver enough ultraviolet radiation to the surface to damage the chemistry of life. But again, the situation is more nuanced than simple models suggest. Planets with strong enough magnetic fields can deflect much of the charged particle flux from stellar flares. Dense enough atmospheres can absorb ultraviolet radiation before it reaches the surface. And life on Earth has shown a remarkable capacity to develop protective mechanisms against ultraviolet damage, from the ozone layer that shields the surface to the ultraviolet-absorbing pigments that evolved in organisms exposed to sunlight. Whether life could get started and persist on a world around a magnetically active small star is genuinely uncertain. But it is not obviously impossible, and the range of conditions under which life has proven viable on Earth, from deep-sea hydrothermal vents to highly acidic hot springs to the interior of Antarctic rocks, suggests that we should be modest about our intuitions regarding what life requires. The newly catalogued low-mass stars in the Pleiades span a range of ages and masses, from objects that might be right at the boundary of brown dwarf and true star to objects that are clearly hydrogen-burning but just barely. Among the older, cooler ones, those that have been around long enough to have settled into the relatively stable phase of their lives when flare activity subsides, the prospects for habitable planets may be better than around their younger, more active counterparts. We cannot currently check any of this. The Pleiades are too far away for our current generation of planet-hunting instruments to detect Earth-sized worlds around individual stars in the cluster, and certainly too far to analyse the atmospheres of any such worlds for biosignatures. But the fundamental work of knowing which stars are there, knowing their masses and temperatures and ages and chemical compositions, is the necessary first step before any more targeted investigation can happen. Every one of the newly catalogued stars is a target that could not be put on a list before it was discovered. There is a second thing that makes the Pleiades particularly interesting as a laboratory for questions about life's potential prevalence, and it goes back to the chemistry we were discussing before. Because the Pleiades are relatively young, 100 million years old, the planets around them, if they exist, have had 100 million years to develop whatever chemistry they're going to develop. On Earth's timetable, 100 million years was enough to get from the first multicellular organisms to sophisticated ecosystems with complex animals. It was the time period during which the dinosaurs rose, diversified, and then were wiped out by the impact that ended the Cretaceous period. It is a significant stretch of time, enough for substantial evolutionary and geological change, enough for life to establish itself and begin transforming a planet's environment if it is present. But it is not enough for the kind of long, patient process that produced complex intelligent life on Earth, if current theories about that process are correct. Earth's biosphere took about 4 billion years to reach its current level of complexity. Simple life appeared relatively quickly after the surface cooled and liquid water became stable. But complex multicellular life took 3 billion more years to emerge from that simple beginning, and tool-using, language-speaking intelligence took hundreds of millions of years beyond that. If these timescales are typical rather than extraordinary, then a 100 million-year-old planetary system around a Pleiades star would be at approximately the stage Earth was at, when the most complex creatures were still primitive marine animals. Interesting biology, potentially if it is there at all, but not civilizations. This matters for the Fermi paradox, which we touched on earlier. One way to partially resolve the puzzle of cosmic silence is to note that most of the stars in the universe are either very old and formed in an era when the interstellar medium was not yet chemically enriched enough to build complex rocky worlds, or they are very young and simply have not had enough time yet for the development of sophisticated life. The era in which our solar system formed, roughly 4.5 billion years ago, was actually a somewhat privileged moment in the galaxy's history, late enough that the interstellar medium was well enriched with heavy elements from earlier stellar generations, but not so late that the galaxy's star-forming activity had significantly declined. Stars forming now in young clusters like the Pleiades are chemically rich enough to build complex rocky worlds, but they are too young for complex life to have emerged on those worlds, assuming our own case is representative. In another 4 billion years, the low-mass stars of the Pleiades might host worlds with mature biospheres, complex organisms, perhaps even technology. But we're not going to hear from them anytime soon, unless, of course, the timescale for the emergence of complex life on Earth was unusually long, not unusually short. If intelligence can emerge in 1 billion years under the right conditions, or 500 million years, or even less, then a 100 million-year-old planetary system might already be well on its way. We genuinely do not know the typical timescale because we have exactly one data point: Earth. One data point is not enough to determine a typical timescale for anything. It could be that Earth was unusually fast. It could be that Earth was unusually slow. Without other cases to compare it to, we simply cannot tell. This is the fundamental limitation of Earth-based astrobiological reasoning. Everything we know about the development of life we know from one example. Every principle we extract from that example might be a universal principle, or it might be a quirk of our particular case. The only way to break this deadlock is to find other cases, either life elsewhere, detected through biosignature chemistry in a distant atmosphere, or the absence of life in environments where it should be present if the timescales are short, or the fossil record of a dead biosphere on a world that once had life but lost it. Any of these would dramatically sharpen our picture of how common and how fast life is. Venus, again, is relevant here. If Venus once had liquid water and a biosphere that was then sterilized by the runaway greenhouse, the chemistry of that ancient biosphere might have left traces in Venus's rocks, fossilized remnants of organisms or their metabolic products preserved in minerals that survived the transition to hellish conditions. Finding those traces, if they exist, would be one of the most significant scientific discoveries in human history. It would tell us that life arose independently in our own solar system, which would make the case for life's prevalence throughout the universe enormously stronger. The absence of such traces, if a thorough search fails to find them, would not definitively rule out an ancient Venusian biosphere. Preservation depends on many factors, and billions of years of geological activity might have destroyed the evidence. But absence of evidence, while not evidence of absence, is at least a data point that shifts the probability estimates. Meanwhile, there is Mars. Mars is currently dry, cold, and bombarded by ultraviolet radiation because it lost its magnetic field billions of years ago, allowing the solar wind to gradually erode its atmosphere. But Mars was not always like this. Early in its history, Mars had liquid water on its surface, flowing rivers, persistent lakes, possibly an early ocean covering much of its northern hemisphere. The conditions for life, as we understand them, were present on early Mars for at least a few 100 million years. Whether life arose during that window is one of the great unanswered questions of our time. The missions currently operating on Mars, and those planned for the future, are designed to search for chemical and mineralogical evidence of ancient life, looking in ancient lake beds and river deltas where organic material might have been preserved. If life ever existed on Mars, the best preserved evidence of it likely sits in sedimentary rocks deposited in standing water 3 or 4 billion years ago. What makes Mars particularly compelling is that we know life arose on Earth at roughly the same period that Mars also had liquid water and potentially habitable conditions. The two planets were not entirely dissimilar in their early histories. Both had water, both had energy sources suitable for life, both had the chemical raw materials. If life arose on Earth in that era, why not Mars? One answer might be that Mars's habitability window was too short. The loss of its magnetic field and the thinning of its atmosphere may have happened relatively quickly, cutting off the era of liquid water before life had a chance to get established. Another answer is that life might simply be rare enough that having the right conditions is not sufficient, that the right conditions combined with the right chemical accident is required, and the chemical accident did not happen on Mars. Or perhaps it did happen on Mars. Perhaps Mars had life that left traces in its ancient rocks that we have not yet found, and the next sample return mission or the next drilling operation will pull a rock core up from an ancient lake bed and find organic molecules with an isotopic signature that can only be explained by biological activity. If that happens, if Mars's ancient rocks turn out to contain the fossil chemistry of life, then together with whatever future missions discover about Venus's geological history, and together with the emerging ability to probe the atmospheres of planets around nearby stars for biosignature gases, we would find ourselves in a solar system and a galaxy that was not looking like an empty place after all. The silence that puzzled Fermi might turn out to be a silence of our own instruments' limitations rather than a silence of the cosmos itself. The stakes of these questions are enormous, and I want to be direct about why. If life is rare in the universe, if the combination of circumstances that led to life on Earth was extraordinarily improbable, then our existence is among the most remarkable and precious things in the cosmos, and we bear a correspondingly extraordinary responsibility to the universe to sustain it. We might be, in some meaningful sense, the only minds that the observable universe has so far managed to produce. If life is common, if it arises wherever conditions permit and conditions permit on a significant fraction of rocky planets with liquid water, then the universe is inhabited in a way that is deeply reassuring. The loneliness of the cosmos is an illusion of our limited instruments, and our existence is not unique, but is one expression of a pattern that is woven into the fabric of chemistry and physics, operating across billions of years. Both possibilities are astonishing. Neither is comforting in a simple way. Both demand that we take the question seriously enough to pursue it as aggressively as our current science allows. The alignment of Moon and Venus and Pleiades on April 29th was a beautiful reminder that we live in a system, a solar system embedded in a galaxy embedded in a universe that is connected in ways both obvious and subtle. The alignment was geometrically obvious. The connections between Venus's atmospheric story and the climate stability of Earth, between the chemical history of the Pleiades and the origin of the elements in our own bodies, between the question of life in the solar system and the question of life around those newly discovered dim stars 440 light-years away, those connections are subtle. They take knowledge to see. They are invisible to the naked eye, but they are real connections, as real as the alignment itself. There is something we have been circling around throughout this story, something that the April 29th alignment makes vivid in a way that a purely scientific account might not, and it deserves to be named directly. Human beings are unusual in the cosmos not just because we might be conscious, not just because we have developed technology, but because we have this specific habit of caring about things that have no immediate practical value to us. Stargazing, mythology, the naming of star clusters, cave paintings of astronomical patterns, the study of worlds so distant and conditions so hostile that we will never visit them and they will never affect us. The counting of brown dwarfs in a cluster 440 light-years away, this habit of caring about things simply because they are interesting, because they are beautiful, because they are true, is not something that natural selection obviously favours. You cannot eat knowledge of the Pleiades' stellar population. You cannot directly survive on understanding the runaway greenhouse that baked Venus. The impulse to look up and ask what is up there seems, from a certain narrow evolutionary perspective, like a luxury, something that became possible only after the basic survival problems were solved. But I think this reading is backwards. I think the curiosity came first, or at least came alongside the survival imperatives, not after them. The cave painters who scratched the Pleiades into the walls of Lascaux 17,000 years ago were not doing it after they had solved all their problems. They were people with very hard lives, facing predators and cold and scarce food, and they found time to paint the night sky on stone walls anyway. The ancient Babylonian astronomers who compiled centuries of Venus observations were not doing it from comfort and surplus. They were doing it because attending to the patterns of the sky was, for them, a matter of serious importance, intertwined with agriculture and navigation, and the management of civic life. The curiosity and the practical necessity were never cleanly separable. The same attention that produced the mythology produced the calendar. The same attention that produced the calendar produced the navigation. The same attention that produced the navigation produced the science. It was never a luxury. It was always also a tool, the most versatile tool our species ever developed, and now we have built instruments that extend that attention to places and phenomena that no unaided human sense could ever reach. And we are finding again and again that attending carefully to those distant places and phenomena yields knowledge that feeds back into understanding ourselves, our planet, our place in the universe, and the conditions under which life and intelligence can exist. The newly discovered stars in the Pleiades are not going to directly solve any of humanity's immediate problems. Knowing that there are thousands more dim stars in that cluster than we previously thought does not cure disease or end conflict or feed anyone. This is often used as an argument against investing in basic science, against funding the kind of patient, systematic survey work that produced this discovery. But the history of science shows, again and again, that the returns on basic research are real. They are just unpredictable and delayed. You do not know when you do the survey which of its results will matter most in 20 years, or 50 years, or 100 years. You do not know which observations will provide the calibration data that makes a future measurement critical. You do not know which newly catalogued stars will turn out to be the most interesting targets for the next generation of planet-finding instruments. You do the work of understanding as carefully and as completely as you can, and you trust that understanding is useful because the entire history of human civilization is evidence that understanding is useful. And beyond utility, there is something else. There is the simple fact that we live in a universe, and the universe is extraordinary, and knowing more about it is intrinsically worthwhile, in a way that does not require further justification. The Pleiades contain thousands of stars we did not know about. That is true whether or not that fact is ever useful. It is part of the description of the universe we live in, and the description of the universe we live in is the most important thing there is. Now, there is a specific kind of wonder that the April 29th alignment evokes that I want to spend a moment with, because it is something that astronomy does uniquely well and that I think people underestimate. The alignment brought together three objects, the Moon, Venus, and the Pleiades, that are connected to each other across enormous differences of scale, distance, and nature. The Moon is a rocky body roughly 3,500 kilometers across, gravitationally bound to Earth, formed from the debris of a massive collision between the early Earth and a Mars-sized object roughly 4.5 billion years ago. It is, in cosmic terms, right next door. Its light reaches your eye in just over a second. Venus is a planet of roughly 12,000 kilometers diameter, a separate world with its own history and its own chemistry, and its own trajectory of development, separated from Earth by tens to hundreds of millions of kilometers depending on where we both are in our orbits. Its light takes 2 to 3 minutes to reach your eye. The Pleiades are a cluster of stars, the nearest of them considerably larger than the Sun, the dimmest of them barely qualifying as stars at all, separated from each other by light years of space, held together by mutual gravity, located 440 light years from Earth. Their light has been travelling toward your eye for 4.5 centuries. These three things appeared together in a patch of sky you could cover with your palm. The perspective flattened the incomprehensible depths of space into a single plane, turned billions of kilometers of three-dimensional reality into a two-dimensional picture of apparent proximity. And here is what I find most interesting about that. The experience of the alignment, the beauty of it, depended on that perspective. If you could somehow perceive distances as distances, if you could stand in the middle of the solar system and see the Pleiades 440 light-years away, and Venus a fraction of that distance, and the Moon almost imperceptibly close, the alignment would not exist. The three objects would be in different parts of your visual field. The picture would be gone. Beauty, in this case, is a product of limitation. Our inability to perceive the true depths of space is what creates the visual impression that these three objects are neighbours. Our confinement to a single vantage point on Earth's surface is what makes the alignment possible as an experience. This sounds like it could be a melancholy observation. Our limitations create our beauty. But I think it is actually something more interesting than that, because the limitation is not arbitrary. We evolved to perceive the world at the scale and distance where our survival decisions mattered. We see at the scale of faces and fruit and predators and weather. The night sky is a gift of that scale, the one domain of reality where the scales we can perceive, the angular separations of degrees and arc minutes, happen to map onto phenomena that are genuinely interesting and illuminating to observe. We are not too small to see galaxies and not too large to see planets. We are precisely the right size to look up at the night sky and see something comprehensible and beautiful. The Milky Way is not a smear too faint to see. It is faint enough to require dark skies and enough presence to reward the effort. The Pleiades are not too far away to be visible or too close to be impressive. The Moon is not too large to see as a disk or too small to disappear into a point of light. We fit the sky in a way that seems almost designed, and of course it was not designed. It emerged from evolution in an environment where the sky was useful, where tracking the Moon and the seasons and the positions of stars provided real advantages. The fit between human visual capabilities and the scale of the observable universe is one of the more quietly astounding facts about our situation. And the alignment of April 29th made it vivid, because there it was, three objects at three wildly different distances, framed together in a view that seemed almost artistically composed, fitting neatly in the field of vision, available to anyone who stepped outside at the right moment. We should step outside more often. One thing the Pleiades story does, and that the April alignment amplifies, is illustrate the concept of time at different depths simultaneously. When you stand outside on a clear night and look at the western sky, you are receiving information from multiple different points in cosmic history at the same moment. The Moon's light left the Moon a little more than a second ago. The event you're observing with your eye, the distribution of sunlight and earthshine on the Moon's surface, is happening in your temporal neighbourhood. It is nearly contemporary. Venus's light left Venus 2 or 3 minutes ago. In those 2 or 3 minutes, the Earth has rotated slightly on its axis. The Moon has moved a tiny fraction of its orbit. The events you observe on Venus, or rather the light pattern you receive from Venus, are 2 to 3 minutes old. The Pleiades' light is 440 years old. As noted before, it left those stars when Shakespeare was young and the telescope had not yet been invented. The pattern of stars you see is the pattern as it existed in 1585, not the pattern as it exists tonight in the Pleiades' actual present. But here is the thing. The Pleiades' actual present, the state of the cluster as it actually exists right now, at the moment you are reading this, is not something you can observe. It is not something anyone on Earth can observe. It is, from our perspective, inaccessible. The information about the current state of the Pleiades is somewhere between Earth and the Pleiades right now, still in transit, and it will arrive here in 440 years. Future observers, if they exist, will see what the Pleiades look like tonight. We cannot. Every star in the sky that is more than a light second away is, in this sense, a time capsule. We observe stars not as they are, but as they were when they emitted the light we are now receiving. The very distant objects, galaxies billions of light years away, we observe as they were billions of years ago. The universe we see is a composite image from different depths of time, not a snapshot of the universe as it currently exists. This is deeply strange when you sit with it. The night sky is a time machine, not in the science fiction sense of a device that transports you through time, but in the literal physical sense that the images it presents to your eye are images from different moments in the past, combined into a single simultaneous impression by your visual system, which has no way to tag each photon with its age. Ancient light and recent light fall on your retina together. You cannot tell the difference. The moon looks as immediate as the Pleiades. The nearby stars look as contemporary as the distant galaxies. Your eye assembles a picture that feels like the present, while actually being a temporal collage assembled from signals sent at vastly different moments in history. There is something both vertiginous and beautiful about this. You're never really seeing the sky as it currently is. You're always seeing the skies past, at varying degrees of pastness, depending on how far away each object is. The present sky, the sky as all its objects actually exist right now, simultaneously in their own present moments, is not an observable thing from our vantage point. It is distributed across space in a way that no single observer at any single location can ever witness all at once. This connects to something deep in modern physics, to the concept of simultaneity and the relativity of time across distances, which says in part that there is no absolute present, no single moment that is simultaneously now everywhere in the universe. The universe does not have a global clock ticking in sync across all locations. It has only local clocks, running at rates that can differ depending on gravitational conditions and relative velocities, and the concept of now is strictly local. The night sky is, in this sense, a beautiful illustration of a fundamental physical truth. What you see is a function of where you are and when you are, not a view of an absolute reality that everyone everywhere would share simultaneously. Your version of the sky is yours. The view from a planet orbiting a star in the Pleiades cluster, looking back toward our solar system, would be an entirely different temporal composite, seeing our sun not as it is tonight, but as it was 440 years ago, in 1585, and seeing the rest of the galaxy from that particular vantage point's particular depth of time. There is no view from nowhere. There is only the view from somewhere. We are somewhere. We are here, on this planet, orbiting this star, embedded in this part of this galaxy, looking out through this particular slice of space and time at a universe that is older and larger and stranger and richer than any single observer from any single vantage point can fully take in. And yet we try. We have always tried. We scratch patterns into cave walls. We build instruments that see in wavelengths our eyes cannot. We launch spacecraft to other worlds and photograph their surfaces and analyze their rocks and breathe their ancient chemistry through spectroscopes. We count stars in clusters we thought we knew and find thousands we did not expect. We look for phosphine in the clouds of Venus and iron in the spectrum of a star 400 light-years away, and ancient shorelines on a red planet and traces of biology in the light filtering through the atmosphere of a world around a distant sun. We reach with our instruments as far as the instruments can reach, and then we build better instruments and reach further. The April 29th alignment reminded millions of people that the sky is there, and it is doing things, and those things are worth attention. Not because a celestial alignment has any direct effect on human lives, not because the moon and Venus and the Pleiades being close together in the sky means anything about what will happen tomorrow, but because noticing it, really noticing it rather than glancing at it for a second before going back to a screen, is a form of contact with reality that is harder to achieve than it sounds. Contact with the actual size and age and strangeness of the universe is, I think, one of the most important things a human being can do for their own cognitive and emotional health. Not in a vague self-help way, but in a very specific way. The universe is so much older and larger than the scale of any individual human concern that spending time genuinely inhabiting that scale, even for a few minutes, shifts something in the hierarchy of what feels important. Your personal anxieties and conflicts and disappointments are real. They matter. But they exist on a scale that is, in the context of a 100-million-year-old star cluster, containing thousands of newly discovered stars, almost infinitely small. Knowing that, feeling it, even momentarily tends to produce a kind of equanimity that nothing else quite achieves. The universe is indifferent in the way that a vast natural landscape is. Indifferent. Not maliciously indifferent, but simply operating on scales that have nothing to do with you, and that indifference is oddly reassuring. You're not the centre of the story. The story is much larger than you, and that is, properly understood, a relief. Ancient sky watchers must have felt something similar, whether or not they would have articulated it this way. The Pleiades rising in the autumn meant the planting season was approaching. The Pleiades disappearing in the summer meant something else was beginning. The cycles of the sky were larger than any individual life, larger than any single community, larger than the memory of any living person, and yet they were reliable. They would return. Whatever disasters had befallen the community that year, whatever deaths and droughts and conflicts, the Pleiades would rise again in autumn. That reliability was not just practical, it was comforting in a deeper way, evidence that the world operated according to patterns that could be learned and trusted, that the universe was not entirely chaotic, that the present difficulty was situated inside a larger order that persisted beyond it. We have that same evidence, more precisely quantified than the ancient observers could manage. We know the precise orbital mechanics that will bring Moon and Venus and Pleiades together in similar configurations in the future. We know the timescales on which those configurations will repeat, varying slightly each time as the planets move through their cycles, never quite identical, but recognizable. We know the much longer timescales on which the Pleiades cluster itself will evolve, gradually dispersing its membership into the galactic disk, losing its identity as a cluster over the next billion years or so. We know that our Sun will burn for another 5 billion years before expanding into a red giant and eventually collapsing into a white dwarf. We know that the low-mass stars now being catalogued in the Pleiades will outlive our Sun by orders of magnitude, quietly burning for 100 billion years in a universe that will be almost unimaginably different from the universe of today. We know that the universe itself is roughly 14 billion years old and shows no signs of stopping its expansion anytime soon. All of that knowledge is, in a sense, an updated version of what the cave painters and the ancient farmers and the Maya astronomers were reaching for when they tracked the sky's patterns. Evidence of a larger order, evidence that the world operates according to principles that persist beyond any individual life or any individual civilization, evidence that we are embedded in something that is not arbitrary, that has structure and history and a future, even if that future extends far beyond anything we can directly experience. The discovery of thousands of new stars in the Pleiades is, in this light, not just an astronomical result, it is another piece of that evidence. The universe contains more than we thought, even in the places we thought we understood. That excess, that surplus, that persistent tendency of the cosmos to be richer and stranger and more various than our current best picture of it, is itself a kind of order, a meta-pattern in how our knowledge grows. We look. We find more than we expected. We revise our picture. We look again. We find more than the revised picture expected. The surplus persists across every generation of instruments and every improvement in technique. The universe is not stingy with content. It is generous with it, extravagantly generous, in a way that suggests we will never reach the bottom of it, never arrive at the point where all the stars are counted and all the structures are mapped and all the patterns are understood. The project is open-ended. The sky does not close. This is not a cause for despair at the enormity of the task. It is a cause for the opposite feeling, for something like gratitude. There will always be more to find. The next generation of astronomers will build better instruments and look at familiar objects and discover things that were invisible to us. The generation after that will do the same. The Pleiades will continue to yield new information as long as there are instruments capable of asking new questions and observers capable of being surprised by the answers. The Seven Sisters of mythology are in reality a family of thousands, and probably thousands more that even the newest surveys have not yet reached. They are 4.5 centuries old in the light we see from them tonight, but they are 100 million years old in their own lives, and they will outlive our civilization by time spans that have no human-scale analogy. And on the night of April 29th, above backyards and balconies and open fields, they gathered with the moon and Venus in a small patch of evening sky, and people looked up, and some of them took photographs, and some of them just looked. And for a moment the distance between the ancient cave painter and the person standing in a backyard with a phone in hand collapsed to nothing, because they were doing the same thing, attending to the same sky, feeling the same pull of the same ancient light. The universe put on a show, and we watched. And in watching, we were part of it, briefly and fully, the way humans have always been part of it and always will be, as long as there are eyes to look up and a dark, clear night to look into. That is what the alignment meant, not as an omen, not as a message addressed to us specifically, but as an opportunity, the kind the sky offers regularly to anyone willing to take it. An opportunity to look up, to remember the scale of things, to feel, for a moment, the weight of the light landing on your face from 4.5 centuries away, from a cluster of stars that is older than the dinosaurs' extinction and younger than the dinosaurs' rise, from a patch of sky that human beings have been naming and watching and weaving into stories for longer than we have any certain record of. The Pleiades were there before we named them. They will be there after the names are forgotten, and in the time between those two moments, which contains the entire span of human history, and whatever human future there is to be written, we will keep looking at them, counting their stars and revising our counts, reading their chemistry and revising our readings, finding in them a reflection of our own history and our own questions about whether we are alone, and returning to them season after season the way every generation since the first human beings capable of noticing the night sky has returned to them. They are patient, they are ancient, they are full of more than we have yet found. The stars are still out there, and so are we.